So we're going to continue our discussion on correlation of plasticity index and flow index. So the correlation between the two was studied and it was determined by Sridharan and his company. So he stated that the correlation between the flow index and the liquid limit test and the plasticity index is given by this equation. So plasticity index in percentage is equal to 4.12 of the flow index, which is also in percentage. And we have here the graph showing the relationship between the two. Along the x-axis, you have the flow index, and along the y-axis, you have the plasticity index. Okay, after the two Atterberg limits, the liquid limit and plastic limit, we move on to our the last Atterberg limits, which is the shrinkage limit. A shrinkage limit test gives a quantitative indication of how much moisture can change before any significant volume change and to also indicate the change in volume. So the shrinkage limit is useful in areas where soil undergo large volume changes when going through wet and dry cycle. As example to this are earth dams. So basically, shrinkage limit is an indication for a volume change in a particular soil, from wet soil to dry soil. So soil shrinks gradually as it loses moisture content. The point at which the soil no longer shrink is defined as shrinkage limit. So basically, once the soil gradually loses the moisture content, or the moisture content, basically the soil shrink. So soil shrink when it loses moisture content or water content. So however, there is a certain point in which the soil will no longer shrink. And if the soil does not shrink, meaning to say it approximately obtain its peak, so that is now defined as the shrinkage limit. So shrinkage, so we have here our illustration for our shrinkage limit. So you have the volume of the soil. So basically, when the soil at shrinkage limit, so there's a certain point wherein the soil doesn't shrink anymore. It doesn't shrink as it loses moisture content. So basically, that point is what we call the shrinkage limit. So this is our point of the shrinkage limit. So for the shrinkage limit, of course, we obtain this value using by drying a soil sample, a wet soil sample. So meaning to say you have a soil sample that is wet, you dry that one using an oven, you oven dry, for example, and it loses the water content or moisture content. So that is now you can obtain your shrinkage limit. So the formula for the shrinkage limit is this one. You have SL represents our shrinkage limit, which is equal to 100 multiplied to the quantity of M1 minus M2 all over M2 minus B sub I minus B sub F all over M sub 2 multiplied to our density of water. So basically, our M1 and B sub I are the wet soil sample and volume. So for M2 and B sub F are the dry soil mass and the volume. So this is before, this one is before oven drying, this one is after oven drying. So this is the value before you oven dry, and this one is the value after you have oven dried your soil mass. So you have a typical shrinkage limit for a clay. So we have here the values illustrated on the table. So we have here the example. Following the result of a shrinkage limit test, the initial volume of soil in a saturated state is 24.6 cubic centimeter. Final volume of the soil in a dry state is 15.9 cubic centimeter. The initial mass in saturated state is 44 grams. Final mass in a dry state is 30.1 grams. So you're going to determine the shrinkage limit of the soil. So we are given with the initial and the final volume and mass of the soil sample. So we just have to obtain the shrinkage limit. So to obtain that one, you simply have to identify the value for M1, M2, V sub I, V sub F, and of course your density of the water. For this one, since we are in grams in cubic centimeter, that would be 1 gram per cubic centimeter. Once you obtain those values, you simply have to substitute to our shrinkage limit equation, and you obtain now 17.28%. Now we have liquidity index and consistency index. So when I talk about liquidity index, it is used for scaling the natural water content of a soil sample to the limits. It can be calculated as a ratio of difference between natural water content, plastic limit, and liquid limit. So our liquidity index is given by this equation, where W is the natural water content. So the relative consistency of a cohesive soil in a natural state. So it can be defined as the ratio called the liquidity index. So as mentioned, you have this formula for the liquidity index. And as mentioned a while ago, our moisture content, that is the in situ moisture content of the soil. The in situ moisture content of a sensitive clay may be greater than the liquid limit. So in this case, you have here the, you need to say liquidity index must be greater than 1. So when the soil, when remolded, can be transformed into a viscous form to flow like a liquid, the soil deposits that are heavily overconsolidated may have a natural moisture content less than the plastic limit. So we have here the condition. So another index that is commonly used for engineering purposes is the consistency index. So for our consistency, that is important, measurement of the results from pairwise comparison. The pairwise comparison is a method to calculate the weights of each element in order to perform the comparison of the two advantages. So the consistency will be determined through the value of the consistency index. So you have the equation for the consistency index, which is liquid limit subtracted by the moisture content over the liquid limit subtracted by plasticity index. So we have here the illustration for our liquidity index. So this is the line from our plasticity index towards a plastic limit towards the liquid limit. This is the plasticity index. So we have here for when plastic limit for the liquid at the plastic limit, when the liquid limit is equal to 0, and at the point of liquid limit when the liquidity index is equal to 1. So we have what we call activity. So when we talk about, basically, because the plasticity of soil is caused by absorbed water that surrounds the clay particles, you can expect that the type of clay minerals and their proportional amount in the soil will affect the liquid and plastic limit. So it was Skempton during 1953 observed that the plasticity index of a soil increases linearly with the percentage of clay size fraction. So the correlations of Pi with the clay size fraction for different clays plot separate lines. So the difference is due to the diverse plasticity characteristic of various types of clay minerals. So according to Skempton, he has this equation that activity can be expressed as plasticity index over the percentage of clay fraction in weight. So when we talk about activity of soil, of course, it can be defined as a ratio of plasticity index to the clay fraction as percentage. The amount of retained water or state of water in soil mass depends upon available clay mineral in soil. So activity of a soil assesses capacity of soil to hold water. So we have here an illustration for the activity based on Skempton, and these are relationship between plasticity index and clay fraction by weight for a certain type of clay mixtures. So according to Skempton, as shown on the figure 4.16 and 4.17, he can express or redefine activity as plasticity index over the percentage of clay size fraction minus the constant for a given soil. So there was also a study by Polidori for an empirical relationship for the activity of soil. So he has obtained this expression wherein CF is the clay fraction, which should be smaller than 2 micrometers. So we have here the relationship between plasticity index and clay fraction by weight for bentonite clay mixtures, and a simplified relationship between plasticity index and the percentage of clay fraction by weight. So you have plotted here the percentage of clay size fraction and the plasticity index. Then we have, after of course, we have to move on now to plasticity chart. So plasticity chart, actually, it will provide you with a method for determining the type of fines. So in the plasticity chart, we have what we call the A line and the U line. So as mentioned, liquid and plastic limits are determined by relatively simple laboratory tests that provide information about the nature of cohesive soil. So engineers have used to test extensively for the correlation of several physical soil parameters as well as for soil identification. So for these plasticity charts, you have your A line on which separates the clay from the silt. So this is the A line. You have the equation for the A line. This separates the clay from the silt. So this is actually, you have also the equation for the U line. The U line is the upper limit of your A line. So this is the illustration for the plasticity charts. And basically, A line, it separates the clay from the silt. So we have here the legend for the presence of what type of soil we have identified for plasticity chart. So the plasticity chart plots the liquidity limit against the plasticity index of various soil. It is useful for studying the correlation of these parameters and for soil identification. So as mentioned, our A line has this empirical equation. It separates the inorganic clay from inorganic silt, and inorganic clay are above the A line and inorganic clays are above the A line. So organic silts are in the same region as organic silts of medium compressibility, as shown in our plasticity charts presented a while ago. So we have the presence of the U line. It is an empirical relation given by this equation. So it is a line approximately the upper limit of the relationship between the plasticity index and liquidity limit of any known soil. So we have here the shrinkage limit plumb, estimating the shrinkage limit plumb from plasticity index and liquidity index. You have your point A, which is known plasticity index and liquidity index, and point B, which is the intersection of the A line. This is the A line and the U line. Point B is the intersection between the A line and the U line, and this is the presence of point C. This is the intersection of the line AB. With the x-axis is approximately the shrinkage limit. So you have plotted your A line, which has a known plasticity index and liquidity index. And of course, you have your point B, the intersection between the A line and the U line. And once you connect this point A and point B, it will intersect along the x-axis, and that is what we call point C. And this point C is now approximately our shrinkage limit. So basically, that is for, this ends our discussion for plasticity for a certain soil sample.